The researchers were interested in finding out how the students would solve problems involving exponential functions, even though, at this point, their formal knowledge of exponents was very limited.
You may know this puzzle. It's called the Tower of Hanoi. The rules are you can only move one disk at a time. And what else?
You can't move a bigger one onto a smaller.
You can never put a bigger one on top of a smaller one.
For them, this was an unsolved problem. For them, like a mathematician who's working on a problem, they don't know the answer. And even though we know there is an answer, they know that we're not going to tell them what that answer is. So for them, the conditions are very much like mathematicians doing original mathematics.
It's hard when you've got a lot of disks flying around to try to find a way to move these disks without breaking those rules.
23, 24.
I think if you were to start to actually carry this task out, one finds out very quickly that it can get pretty complicated.
1, 2, 3, 4, 5, 6, 7. 3 is 7.
One of the first things that a mathematician does, or often does, is to simplify the situation. Rather than look at the problem in all its complexity, look at another problem. And that problem shares perhaps some of the characteristics of the original problem, but it has many fewer of the complexities. And you would work with that simpler problem to see what one could learn. Hopefully, what you learn in that situation you can apply to the more complex situation.
Okay, I want somebody to come. Suppose we had just one disk. Somebody come and solve that puzzle.
So simplification is an important step.
It has to move at least once.
Okay, and now I need to keep track. When there was one disk, it took one move. Everybody agree with that?
Yeah.
And that's what we've got here, okay? Somebody told me if there were 2 disks, it would take 3 moves. Is that right?
Yeah.
Somebody come and do that. Amy Lynn, can you come do that?
7. That works.
3. Took the 3 moves, okay? So that looks all right. Is that okay?
Yeah.
Happy with that? Okay. Need somebody to come down and do it with 3 disks.
I'll do it for
7.
2,
3,
3, 4, 5, 6, 7. Looks like it's right, huh? Okay. Is that all right? Everybody happy with that? Now, how about 4 moves? Millen, you figured out what it'll be with 10?
That's 9.
It's going to be 9.
I can do 15.
Okay, we need to try this, I think, because we got some disagreements here, potentially.
We better come up because I'm probably going to forget.
15.
I did it in 15.
Okay, Stephanie just did it in 15.
15 too.
Can anybody do it in less than 15?
I found the pattern. I found the pattern with it.
What is the pattern?
Hey, Bill.
It's like, look at it from this way. 2 times 2 times 1 is 3. 3 times 3 plus 1. 4 times 4 minus 1. And I go 5 times 5
You know
plus
the
1.
pattern too.
End the world. 6 times 6 minus
Don't
1.
do that too quickly here.
Like 1 and 1 are 3, and then you add 1 more, and then it's 3 and 3 are 6, and then you add 1 more.
So
and
do we.
7 and 7 are 14, and then you add 1 is 15, and then 15 and 15 are 30.
Michelle and Encore found something very clever, but
31
it may
is
not
the next
end the
one.
world today.
31's the next one.
Another thing that a mathematician does is look for patterns. They look at perhaps many instances, and from those classes of problems that the mathematician is solving, there certain patterns may arise. The idea is, in some sense, to try to understand or somehow summarize what that pattern might be.
This is what we did. 1 plus 1 is 2, and then 1 more is 3. 3 times 3 plus 3 is 6, and then plus 1 is 7. Then 7 and 7 is 14 plus 6.
See, there's 2 between there, it doubles, becomes 4. 4 is between there, it doubles and becomes 8. 8 doubles.
But that doesn't say anything.
Yeah, I know.
But it's...
Oh, please.
So on and so on and so
And
on.
next
Now,
one's
what's the one we really care about? The one that counts
100.
is 100 here, so we want to know what number goes
Okay.
there.
Oh my God.
Maybe if we get 10, we can get like 20 and then 30. 55.
I know
10 is 1,023.
What's the difference between there?
10 is 1,023.
123.
I already got down to
10.
Thanks.
10,
10 is
1,023. Want to work with us, stuff? If you guys are just like off and la la la.
And then do 10 times 10. Not 10 times 10.
no 10.
You got it? Okay, could we get one discussion so everybody can hear, all right? Who's going to do the talking?
All of us.
All of you?
We all did it.
Okay, can you sort of face the rest of the people and tell them what you've got?
We tried to figure out 10, right?
And it was
Equals 100. No, I'm not writing that. So we found in common that 2 to the 10th power also equals 123.
I think 2 to the 10th is 1,023.
See, we figured this out by going through the numbers.
It's 1,024. That's not right. It's 1,024.
because you can't have non-number as last number.
Thank you very much. That's a clever idea.
And then we realized since it'll work like this to this, like why wouldn't it work? Ooh, excuse me. From 2 to 1, 2 to the 100 power.
I just have a. Why can't it be 10,240? Yes.
Thank you.
It's 2 times 2 times 2 and so on until 100.
What are you going to do with
Almost 7 years after this session, Matt, currently a freshman at Virginia Polytechnic Institute, watched and discussed his work as a 6th grader with Australian mathematician Gary Davis.
We're multiplying everything by 2.
Got it. You got the pattern. Right. Now, do you have any feeling when you look at it? Do you have a feeling of reconstructing what you're doing there? Because you're sitting there by yourself.
I just pretty much was sitting there, like, just looking at numbers, you know. I mean, just like with these and what we did here, it's just a lot of just trying to look at patterns and looking at different kinds of patterns.
That's right.
And if you just see, like 2 and 4, you automatically say, all right, that's either adding 2 or multiplying by 2.
Right.
Then you say 4 times 2 is 8, times 2 is 16. You go times 2. Oh wait, and you see, you just, I guess,
So
pick up on things. Yeah.
You're trying different things in your head, and
Yeah.
then it clicks.
Pretty much, yeah.
Yeah. So in a sense, what's on the board's really important to you.
Yeah.
Because that's what you're looking at.
Yeah.
Fern outlined some of the things mathematicians do when they do mathematics. And I think it's very interesting to watch that the children in the tape do some of these same things. They do think of a simple problem. They do look for patterns. They look for finite differences, as you see. They notice the pattern, and they notice that there's an exponential here. They posit, 2 to the n. And that's what mathematicians do. They see these patterns. They pose a theory that they have to go back and test it.